Stations enabled by Virtual Energetic Particle Observatory and the Space Physics Data Facility.
Sorry. Okay, thank you. So space weather that I'm talking about today, from the review talk we heard earlier this morning, I'm thinking about talking about the solar wind particle and energetic particle interactions, weathering. I'm really just here to advertise services, tools that are available to all who are interested in pursuing such things, particularly for energetic particles. I'm happy to find a home within the Dream 2 team over here with Bill Farrell, and so this is a collaborating activity for that. I am the chief scientist for the Space Physics Data Facility, which is a NASA space plasma, particle, et cetera, data archiving and access facility. So it's been around for a long time and will continue to be. I want you to think about you're checking into a hotel in Death Valley and the pool is closed. What are you going to do? And the person at the desk says, you can watch any movie that has ever been made. Okay, and you say, how is that possible? The answer is infrastructure investment. Okay, so this is one of those infrastructures that allows folks, in various disciplines, to find and use space physics, plasma, energetic particle, and other data. It's far too much here for me to describe in detail. The thing that I'm the principal investigator for is the Virtual Energetic Particle Observatory, which is sort of a focus group, for heliospheric energetic particle data, from KEVs to GEVs and things like that, from the history of NASA missions, going far back to the early 70s, and now through the current geospace missions, and Voyager at the edges of the solar system and all of that. So we cover a very large range. One can go to the site, vpo.gsfc.nasa.gov, and find our services. So the picture here, so here we're looking at Voyager 1, the history of Voyager 1 measurements since its launch in 1977 over here, out to where it is, maybe in interstellar space. We don't know exactly, but that's what the Voyager project says right now. So if you're looking at lower energy particles, half MeV protons, obviously you got a big source over here from the sun, from the active sun that has a cycle of every 11 years of solar activity. And so if you're in the inner solar system, this is your major source of energetic particles at these energies. However, when you go to higher energies, hundreds of MeVs to GeVs, the kind of things that we worry about, for astronauts, galactic cosmic ray radiation, the source is from out here, okay? And it varies during the 11-year solar cycle, as you can see, in different ways. So there are competing, and then there's a region here, which of course is far, far out, where at the boundaries of the heliosphere, where particles are accelerated. This is mainly interstellar gas coming in and being ionized and then accelerated, and somehow by the termination shock out here or some other process. But we're really interested here in this region, the solar-dominated region. So this is a product from the Advanced Composition Explorer mission. And this is several years of data, 97 to 2000, that the folks at Caltech et al. Put together. And if you're a space weathering, plasma particle kind of person, what you really want to know is what is the distribution as a function of either energy or velocity or something like that, of the fluxes of these different kinds of particles. And then you can propagate that into a model for chemistry or whatever to do your space weathering problem. And so we have different components here. So at low energies, at peaking around 1 keV this is for helium, oxygen, and iron, and protons are sort of up here. We have, this is the bulk plasma component of the solar wind flowing at several hundred kilometers a second out from the sun, the expanding solar corona. So it has kind of a Maxwellian distribution, which gets broader depending on the heating of the solar wind and its velocity and so forth. And then above that, we have a drop-off, and then we have this kind of tail region here, what we call a superthermal tail region, which shows a reasonably well-organized kind of spectrum here out to MEVs, KEVs to MEVs. This is an important region for some effects that I will discuss in a moment. It is not the lower part here is kind of not well developed in terms of the data that are publicly accessible. There's a lot published on this, but the publicly accessible data, are not very available, and that's an issue that I want to address in some future work. And as we go way out here, the high energy galactic particles, that will just go about through anything, your spacecraft or your Mars shield or whatever, we worry about those. But those have a relatively more constant intensity. So we need to figure out how to shield those. Here we're a lot more worried about time variations. So this is a fluence kind of spectrum. So this integrates over several years. But what this really is a collection of large solar energetic particle events. So those are the ones that are really going to dominate what happens for long-term space weathering, on the moon or asteroids or whatever. And so the little events, are interesting scientifically, but they don't play much of a role in space weathering. And of course, the really big single events, an astronaut is going to have to worry about because, you got to run for cover. You got to, dig your hole. So this is just a set kind of model spectra. I just want to illustrate there's a big difference between this kind of a 1AU spectrum here, which has this strong superthermal component, and there's some other models for other stuff here, and another kind of spectrum which falls off very sharply down to about 1 MeV, has a big minimum down here, and then we rise up as we start seeing the galactic outer heliospheric cosmic rays. So there's a big difference in the space weathering effect between this kind of a spectrum and something like this, where you have a very strong superthermal component. And I just quickly, so if you imagine, how long does it take to accumulate a certain dosage? In this case, 60 billion rads, which is enough to break every molecular bond in a material. So this is a time scale to do that. If you're talking about galactic cosmic rays, it takes a long time. It takes billions of years. So the high energy stuff penetrating to great depths here, meters and more, that takes billions of years. But the low energy stuff, which has much higher intensity, but is less, it just penetrates a small depth in material, and the microns, that can make changes happen, in thousands of years. And so you're dealing with a vast scale of dynamic range here in terms of time scales as a function of depth and the kind of radiation you're dealing with, to do modeling of space weather processes. This is just a big quick picture of one of our browser surfaces for protons and helium, which you can choose from many different spacecraft here, from ACE to Stereo, Voyager, etc., which are many of the major mass emissions over time, and you can select data from the period, of the inner solar system and look at those. And this is another one where we can actually show we actually have, for certain sources, we have full elemental distributions, out even through nickel here, iron and nickel, from some sources, including ACE. So that's important for space weathering studies. This is just an example of a plot overlaying some Voyager 1978, inner solar system data with some IMP-8 Earth orbiting satellite data, just to give an idea what kind of product you get out. You get some error bars and so forth. And you can compare the spectra from different sources. You can check the calibrations. One new way we're working on doing this is by showing scatter plots. So here's a channel over here for 5 MeV protons, and then here's one for 2 MeV protons, and you can track how those two channels correlate as a function of intensity. In this case, this is a very relatively well-behaved kind of power law type distribution, so that's why you get a relatively linear log-log correlation there. You can look for other times when things are not so well behaved. This is just some examples of heavier things up through iron, showing those spectra here that you can do. And you can do this over an arbitrary period of time if you want to look at a short-term event or you want to look at very long-term averages like over solar cycles. And that is why we have created this tool. I found this on a trip recently to Berlin, at the Berlin Wall. Of course, our mascot here, for cosmic rays and energetic particles is Godzilla here, this is a huge problem, of course, for human exploration. This is this is a big knowledge gap, if you will, about how to model these things and how to deal with them, how to shield against them, how to allow astronauts to survive. It is a interdisciplinary problem between planetary and heliophysics and astrophysics and so forth. And so this is a job for the Avengers, which are guys that have superheroes with different skill sets. So that's the kind of approach we're going to have to take to solve these problems. Thank you.
Questions?
Yeah, Larry Taylor, University of Tennessee. We actually took lunar soil at the Heavy Ion Medical Accelerator in Chiba, and we took, using 200 megavolt iron 56, we actually determined that you could actually retard most of the energy within 25 or 50 centimeters, sorry,
Yeah.
lunar soil.
Yeah,
So
right.
it's much easier to do than we had thought. We had always thought it was going to take a whole lot of burial, but it may not.
Well, iron, of course, loses energy very rapidly. It's less easy for, let's say, protons, but it depends on what's important for the damage.
Yeah, the problem always is neutron generation that we have to worry about.
Yeah, right.
Other questions?